Filaments and basins. Geometric selection in structure formation. One of the most striking features of large-scale structure is not simply that matter clusters, but how it does so. Matter does not distribute itself randomly, nor does it collapse only into isolated clumps. Instead, it arranges along extended filaments that intersect at dense nodes, forming a connected network. This section explains that pattern without invoking exotic assumptions or reinterpreting established models. The claim is simple and structural. Filaments and clusters arise because matter traces convergent curvature basins inherited from space-time geometry. The pattern emerges through geometric selection rather than active attraction alone. To see this clearly, it helps to focus on geodesic flow rather than force-based intuition. In curved space-time, families of geodesics can either diverge or converge depending on the underlying geometry. Divergent regions spread trajectories apart, while convergent regions funnel trajectories together. These properties are not created by matter moment to moment. They are features of the curvature field itself. When matter enters a region where geodesic flow converges along preferred directions, it naturally organizes into elongated structures. Filaments are the visible trace of these convergent pathways. Filaments are stable because they are not accidental alignments of matter, but dynamically preferred routes through the geometric landscape. In a convergent basin, small deviations in trajectory are corrected by the geometry. Matter that strays slightly is guided back toward the filament rather than dispersed away from it. This makes filaments robust over time. They persist, not because matter actively holds itself together, but because the geometry continues to favor those paths. In contrast, regions where geodesic flow diverges do not retain matter easily. Matter passing through such regions spreads out rather than accumulates, leaving them comparatively underdense. Clusters and nodes appear where multiple convergent pathways intersect. These intersections represent deeper basins in the geometric structure, where convergence occurs from several directions at once. Matter arriving along different filaments is geometrically guided into the same region, leading to high-density nodes. Again, no special attraction mechanism is required beyond the existing curvature. The clustering is a consequence of geometry selecting where persistence is possible. This framing does not conflict with lambda CDM observations. Standard cosmology already predicts filamentary structure through gravitational instability acting on initial conditions. What is being clarified here is not the prediction, but the interpretation. The formation of filaments can be understood as matter responding to inherited curvature patterns rather than as matter actively sculpting structure through mutual attraction alone. The equations remain the same. The observations remain the same. What changes is the emphasis on geometric constraint as the organizing principle. Crucially, this explanation avoids stepping into adjacent debates. It does not reinterpret dark matter, address rotation curves, or explain voids, which are treated separately. It focuses narrowly on why filaments and nodes form and why they are stable. By isolating this mechanism, the argument remains clean. Filaments are not evidence of exotic physics. They are the natural outcome of convergent geodesic flow in a space-time geometry that carries inherited structure forward. Seen this way, large-scale structure formation is less about matter aggressively pulling itself together and more about matter being sorted by the geometry it inhabits. Filaments emerge where the space-time terrain channels motion. Nodes form where those channels intersect. The resulting network is not imposed from outside the theory, nor does it require additional assumptions. It is what geometric selection looks like when matter traces curvature over time. Modern structure formation theory already supports the idea that filaments and nodes arise from convergent geometric flow rather than from local attraction acting alone. In general relativity, the motion of matter on large scales is governed by geodesic flow in a curved spacetime. Families of nearby geodesics can either converge or diverge depending on the curvature tensor of the region they traverse. This behavior is formalized through the Raychaudhuri equation, which describes how congruences of trajectories focus or spread under curvature. Where curvature induces convergence, trajectories naturally funnel together. Where it induces divergence, matter disperses. Filaments correspond to regions where convergence occurs preferentially along one or two dimensions, producing elongated structures rather than spherical collapse. This geometric focusing does not require matter to actively sculpt the pathways it follows. Once curvature gradients exist, even weak ones, geodesic flow becomes anisotropic. Matter entering such regions is guided into stable channels where small deviations are corrected by the surrounding geometry. This explains why filaments are long-lived and resilient. They are not fragile chains held together by fine-tuned attraction, but dynamically selected routes where motion remains coherent over time. Perturbations tend to be damped rather than amplified, which is why filaments persist even as local conditions change. Numerical simulations of large-scale structure formation implicitly demonstrate this mechanism. In standard lambda-CDM simulations, matter evolves under gravity from initial conditions and naturally forms a filamentary network. While these simulations are often described in force-based language, the underlying mathematics is geometric. Matter follows trajectories determined by the evolving metric, and filamentary structures appear where the gravitational potential induces directional convergence. The simulations do not require special filament building rules. Filaments emerge automatically from geodesic focusing in the large-scale potential. This is consistent with the interpretation of filaments as geometric attractors rather than constructed objects. Clusters and nodes arise where multiple convergent flows intersect. In geometric terms, these are regions where curvature induces convergence along multiple independent directions. Matter arriving along different filaments is funneled into the same basin, producing dense nodes. This behavior mirrors well-understood focusing effects in curved spacetime, where congruences intersect at caustics. Importantly, this intersection does not require synchronized attraction between all participating matter elements. The geometry itself coordinates their arrival. Observationally, the stability and coherence of filaments across vast scales supports this view. Filaments maintain alignment over distances where local interactions would be insufficient to enforce structure. Their persistence reflects global constraint rather than short-range bonding. Matter flows along them over cosmic time, indicating that they are preferred pathways embedded in the gravitational landscape rather than transient aggregates. Nothing in this interpretation contradicts lambda-CDM observations or predictions. The same data are explained, the same simulations apply. What changes is the explanatory emphasis. Instead of treating filaments as the product of matter aggressively pulling itself together everywhere, they are understood as the natural outcome of matter tracing convergent curvature basins already present in the space-time geometry. Attraction still plays a role locally, but selection occurs geometrically. By grounding filament formation in convergent versus divergent geodesic flow, this framework remains fully compatible with established theory, while offering a cleaner, conceptual account of why structure takes the form it does. Filaments are stable because geometry selects them. Nodes exist because geometry funnels matter into shared basins. No exotic assumptions are required. Matter simply follows the paths that spacetime allows.